All right. Now on to E and M. So, my first thought when I looked at this question is what the hell is this, College Board? It just looks like a nightmare in the making. We got a finite rod, we have a sphere, so many non symmetric situations. But it turns out that if we just read the problem, this actually is not bad at all. And I actually really like this problem. So we got a non-conducting rod of uniform positive linear charge density. It's near a sphere with a negative charge. The rod and the sphere are held at rest, so it's a statics problem. We're given a bunch of equipotentials and 5 labeled points. First up, find the flux through the Gaussian surface whose cross section is the negative 20 volt equipotential line. So here's our equipotential, negative 20 volts. And if we look at that, we can pretty easily tell that there's some sort of Gauss's law thing going on because we have a surface and we have a charge inside of it. So that's our clue that Gauss's law is involved. So we have two definitions, or sorry, we have two ways of really calculating the electric flux. So the definition of electric flux is just the actual textbook definition of what flux is. It's just the dot product of the field and the area vector added up. But the issue here is that this rod causes a bunch of non-symmetric things to happen. So if this sphere was just here by itself, we could just do the E field times the area and get an answer pretty easily. But we can't do that here. But we have Gauss's law, which says that instead of actually computing the surface integral, you could find flux just by taking the net charge inside divided by epsilon 0. And we want the magnitude, so we have a 2 nanocoulomb charge inside. Doesn't matter that it's negative. And epsilon 0 is our typical value of 8.85 times 10 to the minus 12. So let's see, what is this? Well, checking my notes here, it's 226. And the unit is the electric flux. So what is that? Well, let's see. E field is newtons per coulomb. And an area is square meters. So we get Newton per coulomb times meters squared. Lovely. All right. Now, guess we're freaking 10-year-olds now. We have energy bar charts. So back to middle school we go. Okay. Positive test charge placed at position C. An external force is applied to the test charge. I think we potentially need to know that it's positive. An external force is applied, and it moves the test charge to positions in order of C, E, D, A. So we start at C, then we go to E, then we go to D, and then we go to A. And again, it doesn't matter how you get there due to conservative forces. Draw a bar to represent the relative absolute value of the work E to D in comparison to work C to E. So let's figure out what the work done in each segment is. So CE. Well, C is at negative 20 volts, E is at 0 volts. And again, we know that work is equal to Q times delta V. And again, since we're just doing relative magnitudes here, we're just going to be interested in how many volts are changing between each one. So we go from negative 20 to 0, which means that this is 20 units of energy. So that means if we were to scale our axes here, this would be 20, which means this is 10. All right. Work done from E to D. Well, this is easy, because if you're going from E to D, that is on the same equipotential. And how much work does it take to move along the same equipotential line? 0. Again, don't forget the mechanical analogy. If you're just walking around at the same level, the same surface, you're not changing your height, so you're not changing your energy. So you're just going to the same height. Then D to A. Well, D to A, that definitely does change. I'm at 0 volts and I go to 10, 20, 30. So I go from 0 volts to 30 volts, which means my change is 30. So notice that's higher. So I got to go up to 30 here. And then the bar chart, it's just gonna go like that. So there's 10, there's 20, and there's 30. Lovely. Calculate the approximate magnitude of the x component of the electric field. So I knew we were going to have to calculate this of some sort when I saw this question because I knew they gave us the tick spacing. And if you're ever given distances on an equipotential map, you are probably going to have to estimate the E field. So we know that the E field in any direction is equal to the path of quickest descent, which is the negative of the derivative of the potential. So if we're just estimating E sub x and we want the magnitude of it roughly, I'll change this to some approximate symbols for us. Is approximately equal to the magnitude of change in volts over change in distance. Just a nice little delta here. So we just got to find near position B a change in volts and a change in position. So we're given that the tick spacing is 0.4 meters. And I need to really find a distance here. So I could either get this distance, which is 10 volts. I could get this distance, which is 10 volts. But none of those seem ideal right now. So if I actually go over here, that distance is going to be 0.4 meters. So if you had your actual ruler, this would be helpful. So I have the power of just clicking this around. So that's 0.4, and that's 0.4. So it's pretty close to 0.8 to get from the 20 volt to the 0 volt. So that's roughly 0.8 meters, and the delta V is approximate. Well, the delta V is 20 volts. So if we go back over here, we got a 20 volt change, and that's occurring over a 0.8 meter distance. So the rough magnitude of that is going to be roughly 25 volts per meter. Or Newton per Coulomb, same unit. All right. Positive test charge is placed at point D. The test charge is released from rest. Indicate the direction, not components, of the net electric force immediately after it's released. So we're looking at position D, which is right here. So we are asking, where does the force point? So it's a positive charge. And really, there's only two options. So we know that the E field points out of the equipotential line. So we have two options. It's either down or it's up. It's perpendicular to the equipotential. But since this is a positive charge, positive charges experience a force to send them to lower potential, and the lower equipotentials are located in the above direction. So it's in the plus y direction. So why is this true using physics principles? Well, E points perpendicular to equipotential lines. And also, E points towards lower potential and positive charge experiences force along the E field. If it was a negative charge, it would be the opposite, because negative charges go against the E field. So I knew we were going to have to do something with this rod. And here it is. The electric potential VP at X sub P. So that's some point out here. So this is X sub P. And then we're interested in deriving this expression for the electric potential. So to start, realize that since we have a rod and it tells us to use integral calculus, we have to chop this rod up into a bunch of little DQs, because each of these parts of the rod is going to contribute a tiny bit towards the potential. So we know that a tiny piece of the potential is equal to K times the tiny chunk of charge divided by the distance to the point in question. And since we're dealing with a nice linear charge density, dq is just lambda times dx. So we can just do that common replacement here. So that means that the total potential is just going to be k times lambda, because neither of those change, times the integral of dx divided by r. So now we got to figure out what our r variable is going to actually sweep between here. So let's see. So I'm going to define my variable. There's a couple ways of doing this. I'm going to define my variable x as the distance from x sub p to the rod segment. So we're going to call this distance right here x. So I just need to find the largest distance x can be and the smallest distance x can be. So I think it's pretty clear that the largest distance x can be is this xp value. Because again, that's the farthest dq is xp away, so we can do that. So, and x ranges from something to xp. What's the minimum that x is? Well, let's see. xp is the whole distance. The rod is 4L, so it's xp minus 4L. So after integrating, we get k times lambda times ln of x evaluated from xp minus 4L up to xp. And we get k lambda ln of xp minus ln of xp minus 4L. And then anytime you're dealing with integrals and logs, you can typically apply some sort of a logarithm property. And of course, we got the subtraction rule. So for logs, subtraction turns into division. And that is our electric potential as desired. All right. Sketch the graph of the x component of the E field at a distance x away in the region x4L to 12L. So there's kind of a guesswork way of doing this and then the more analytical way. So first, we can reason that as you go farther out, the electric field is obviously going to decrease. So I know that eventually it's going to sort of decrease. But now I got to figure out what's going on near 4L. So again, due to the fact that electric field is depending on distance from each of these DQs, if you're all the way up against the rod, your E field is going to be practically infinite. So we actually get some sort of an asymptote up here. And our E field graph is going to look something like this. All right. So the other way of doing this would just be to kind of look at a graph of V. So V is like kind of like ln. Ln x looks like this. And well, if ln x has a vertical asymptote, that means that over here, the slope is going to be infinity, and it's slowly going to decrease. So if we graph slope as a function of x, we get that. Oh, and then we're done. Nice.